Assalamu alaikum. This is the second video of the second chapter, linear momentum. Hope you have studied the first part very well. At the end of this video, you're going to be able to apply the general form of Newton's second law. Let's remember what we took in the first video. We said that the linear momentum of a particle is p vector equals to the mass times v vector. The linear momentum of a system of particles is p vector g equals to mvg equals to the linear momentum of the system of particles. General expression of Newton's second law. We know that a force applied to a body changes its velocity and therefore its linear momentum. And the more rapid the variation of the linear momentum, the stronger the force causing this variation. Then both F and the variation of linear momentum affect on each other. This variation is governed by the general expression of Newton's second law as the sum of F external equals to the variation of the linear momentum dp by dt. But p is a function of mass and velocity. If the system is of constant mass, then dm by dt, or the derivative of mass, equals to 0. And now dp vector by dt is simply just m into dv vector by dt, which is m times the acceleration, like the case of the motion of a ball or a marble. Then the sum of F external equals to the mass times the acceleration of the center of mass g. And this is the theorem of the center of mass. Keeping in mind that the sum of internal forces between the particles of the system is 0. Now, what if the system is of changing mass? Then the variation of mass is not 0, like the case of a launching rocket. In this case, the change in mass is due to the combustion of gas. We say that dp vector by dt equals to the mass times the variation of the velocity plus v vector times the variation of the mass. Application 1. A solid of mass m equals to 5 kilograms can move on a trajectory situated in a horizontal plane. It starts from rest at instant t0 under the action of two forces, F1 and F2. Determine at any time t the linear momentum of the solid in the frame OIJ vector. We're going to write the general expression of Newton's second law. Since we have forces and linear momentum, the relation between them is F external equals dp by dt vector. What are the forces acting on this solid? It's F1, F2 plus weight and normal, but W plus N is 0 because they are vertically opposite to each other. Then we add the vectors of F1 and F2 and we get 15I plus 25J, which is equal to dp vector by dt. But we want to find the linear momentum, so we make antiderivative of the sum of forces, and it is 15 ti plus 25 tj plus constant. At t equals to 0, the linear momentum is 0, then the constant is 0, and finally the linear momentum is given by 15 ti plus 25 tj kilogram meter per second. Deduce the velocity of its center of mass g as a function of time t. We have found the linear momentum of the system as 15 ti plus 25 tj vector, whereas this expression is equal to mass times vg vector, which is 15 ti plus 25 tj. Divide this linear momentum by the mass, which is 5 kilograms. The answer of the velocity vector is 3 ti plus 5 tj. Conservation of linear momentum. Consider a system at rest. The forces acting on the system are the normal reaction and the weight of the car. The sum of these two forces is 0. And consider another system, the car, moving, and the forces acting on it are the normal reaction, the weight, the motive force, and the friction. The sum of all these forces is 0. In both cases, we say that the system is isolated. For isolated systems where F external equals to 0, we say that dp vector of the system by dt equals to 0 vector. Thus, P vector is constant because the derivative of constant is 0. Here we say the linear momentum of an isolated system is conserved. Thus, P vector of the system initial equals to the P vector of the system final. Note that we say that dP vector by dt equals to delta P vector by delta t when the linear momentum varies linearly with time, where P equals to AT plus B. If we derive it, we have the constant A, and if we make the variation delta P by delta t, it will be the slope of this equation. Also, if the time interval delta t is very small, then delta t goes to 0. Then if one of the above two cases exists, then delta F external can be written as delta P vector over delta t. To sum up, the linear momentum is given by P equals to mass times V. If it's for a system, then Pg equals to mg vector equals to the P vector of the system. The general expression of Newton's second law is the sum of F external vector equals to dP vector by dt. The theorem of center of mass is sum of F external vector equals to m a vector g. And finally, the linear momentum of an isolated system is conserved. Then P vector of the system initial equals to the P vector of the system final. This is the end of the second part of this lesson. Please take notes and study them.